Alright, I think I'm making a video. I better be sure. Okay, looks like it. See if it freezes and crashes and whatever. Alright, so anyway, a few subjects maybe. See how it goes. And so I thought I would just mention a couple of things that were a little bit strange or weird. So the Tybes girl quit her PhD program. And you know, I guess you could make the argument that I guess if you're going to get 141,000 views just for saying you quit, you know, you went to college for, no, let's just say, yeah, I don't know, you know, I mean, what's the difference, right? I mean, as a practical matter, maybe you don't need a PhD, you just need to have some knowledge in physics to get a job anyway, a decent one. And maybe teaching isn't all that much fun anyway, so who knows? Because that's all you'd need the PhD for, usually. Well, who knows? I don't know. It was a weird PhD program anyway, some sort of physics connected to biology or something, which I think is really a stretch. But anyway. But, you know, so it's basically YouTube, you know. She's seduced by the... It's so much easier just to be a YouTube personality, yeah, especially if you're a chick, pretty, all that kind of stuff. So it is kind of disappointing in a way, just because that's sort of just a sign of the bad times, and that much of the talk around physics or the interest in the subject is by people who really don't know anything about physics. And they just want to hear stories, you know, about fancy verses and, you know, mumbo jumbo. It seems, anyway. It's either they're so lost in the deep mathematical, abstract garbage like the PBS videos, or, you know, they want the hopeful, I don't know, there's, oh, the universe is mysterious and interesting, you know, versus mechanical and grindy, you know, kind of view. Anyway, I just thought that was curious, that, you know, kind of a strange thing, YouTube killing, you know, in a sense, just making the world a little tiny bit more dumb, you know, just, you know, you say just a little bit less when people are discouraged from becoming a real physicist, let's say, and just become a YouTube physicist instead. But anyway, alright, so this Steve Scully guy is another kind of story here. You know, he did make a video sort of replying to one of my videos, but it wasn't, I don't think, in any real sense, a reply, just because it didn't get into anything specific to what I was saying. It was just specific to what he was saying, which sort of is fine. I mean, that's what I pretty much do. But I'm right and he's wrong, so obviously it makes a difference. So he's done a couple of others. I haven't watched these yet, where he's reacting to other people's videos. This dissident science one should be fairly entertaining, so maybe I'll play that later. We'll see how it goes. Some of it, just because I'd be curious to see what he disagrees with, in a sense, because he seems to have the same view of the universe that the dissident science guy does, which is somehow he thinks this infinity thing is important, and you know, and this idea that somehow it's a Horton Hears a Who-averse, you know, where the universe replicates itself, you know, in some kind of fractal kind of way, that somehow the underlying micro universe is in some way a duplicate of the bigger functions. Inconvenient. Sorry, alarm clock. I don't know why I needed to be alarmed at this moment, but apparently I did need to be alarmed for some reason. So, sorry. It's been a rough couple of days. So yeah, so anyway, so that should be interesting. Just because so far I haven't found too many differences between the two theories. There was something, but I can't remember what it was. But they also annihilate charge, which is just such a fundamental function, and they both pretend it doesn't mean anything. That somehow they can just create something that's just saying, I'm repulsive, or I'm attractive at will by some mechanism. And there's really no evidence that that's how charge works. It seems pretty clear that electrons stay electrons, and that protons stay protons, and they're only repulsive to each other, and they're not repulsive to everything else, kind of thing. So it really, I think it's very thin and completely inadequate just to say it's high pressure and low pressure. Well, how does it change? How do they know what's high pressure and low pressure? So unless you make two forces, I don't think you can do charge. I tried to do it and it didn't work. So I'm just telling you, you come up with two forces, it all falls into place. It gets really easy. So anyway, it has a couple of these reaction videos that I will try to watch. So the other interesting thing was the Saturday John Chappell, whatever, natural philosophy terms I just can't stand, was sort of interesting because a guy kind of Clive Tickner, did a kind of just diagrammed a lot of the paradoxes about the time dilation relativity theories, and specifically to the ones related to velocity. I would argue that it doesn't matter. The ones related to gravity are really about velocity also. There's nothing about gravity except the fact that it imposes velocity that really has anything to do with time dilation. But anyway, so twin paradox stuff, trains, different kinds of those. So it was interesting, and every time I see it, somebody showing the mirrors and the photons that know how to move forward and all those kind of things, you just say the universe can't possibly work that way. And this is something that just is amazing that it has such staying power as a theory, just because it does create these circumstances that I think are just, they do violate fundamental rules of kind of conservation of momentum and whatnot. So anyway, so that was sort of interesting, just pointing out. Yeah, okay, that's about all I got to say about that. And I think that was it. The rest of the stuff wasn't so interesting. The Rational Science did a video ragging on some Harvard paper that was written about that weird asteroid, but that was before they got the new pictures. So I'm sure whatever the publication was won't be published, because obviously the new pictures indicate it has nothing to do with what was being speculated. But I mean, it was just pointing out how these people running departments at very prestigious institutions are attention whores, and they really don't care about physics and having any integrity, which is sort of again demonstrated by that Kip Thorne guy, being connected with the whole LIGO thing and nobody finding anything wrong with that, in the sense that it's a guy who made a movie about gravity where none of the elements of the movie have anything to do with gravity. I mean, nothing realistic or real in the movie. Every single premise was outside the bounds of reasonable understanding of physics. Alright, so that has been what I've been doing. So the Steve Scully guy does have a book, okay, he wrote, and he does read it online, which is kind of nice. So I've been listening to it while I do this or that, and I'm up to chapter 3. But he really hasn't demonstrated anything with any kind of convincing argument or evidence, in my opinion, to justify infinity, or some notion that charge isn't as big a deal as it is in terms of you really do have to explain how two forces can create the phenomenon. And what else does he say? Obviously you get into faster than light because these underlying forces have to go much faster. And, I'd argue this creates all kinds of paradoxes. And in terms of how how one universe would affect other universes. If you go with this infinite little universes all the way down thing, you have to kind of understand that if they're all dependent or built on top of a smaller universe having some kind of function, then one universe, with the law of probabilities, there's a probability with all those universes one of them would be turn into a bomb or something. It would blow up, and why wouldn't that cascade into all the other universes and blow them all up? And there's sort of lots of paradoxical thoughts you can have when you have any kind of interdependency between those functions, and you have an infinite amount of time. Then you sort of have an infinite ability. You sort of have a inevitable ability to create too many cascading errors for the systems to survive. But again, these people are all religious, is what it really comes down to. I think at the end of this, the punchline in the end of his whole perspective is some sort of God theory. So, whatever. But even that's a good example of, how kind of pointless using God or even infinity as an answer, because you could just say, so I could ask the question, where did God come from? Somebody could say, well, he's the most recent occurrence of an infinite number of God generations. So instead of having one God that lived forever, you could have a God that just keeps getting born over and over and over and over and over, forever and ever and ever and ever. But again, does that answer the question? Does that solve any problem? Because don't you still, even with an infinite universe, still have to have a first universe, technically? I mean, how's that going to work? The simple argument I would make is that we know that complexity has to be made by, you sort of need at least two things, right? You need time, and then you need stuff. So you need enough stuff, to make something complicated, and then you need time, and you have to have enough diversity in the system to be able to create enough change to create anything complex. But I mean, once you can create complexity, then you're also, like I said, you're just opening the door to complexity that, somehow devours your all your universes get eaten by some kind of super virus. If you have an endless or an infinite amount of time and any degree of motion for complexity. I mean, if you have an open window to this complexity, then some of it can go very wrong. Alright, but anyway, who cares? I don't think it's a important subject, but I mean, there's probably lots of arguments that can be made why infinite universes don't make sense, but I just don't know if I want to waste my time trying to explain them all. I think for certain they can't make these simplistic comparisons and try to equate a planet with, say, an electron. I don't think that makes any sense. They clearly don't function on the same level or way. There's no evidence in the big universe of quantization, and the forces that seem to be acting in the big universe seem to be exactly the same forces affecting us. That is, the photons on the big planetary galactic scale are the same photons that are affecting us. So why would I assume they're any different than the same photons that are affecting the tiny universe? So you can't really do the Hoobies can't be living on a dust spot, and they can't be living on an electron. You have to go all the way down to like a photon and put the Hoobies living there. Like that would be what you're comparing to an Earth. Would be like our whole universe is a photon, something like that. And again, that's just all made up. So if it has to be entirely made up as an idea, why bother with it? It can't possibly be relevant. I mean, if our whole universe is just one photon in another universe, clearly almost anything could happen and it wouldn't matter. I mean, if I actually did destroy a photon in the universe, who cares? One photon ain't gonna make any difference. Ain't gonna create enough change to blow up anything. So clearly nothing could ever bleed from one universe to another. So it could never be relevant or meaningful. Alright, so the things I would argue for are the idea that the universe is oscillating, the Big Bang is probably an exaggeration, and what is happening is that I think there's a clear exchange between things becoming denser, the matter bits, getting closer together and being held together by force, and then the force in the free universe. So as the matter gets more and more condensed, more and more force is locked in the matter, and therefore there's less gravity. And then when there's less gravity, that means everything wants to expand, and that's the yin and the yang, is that the universe goes from having more gravity to having less gravity, and then more gravity, and then less gravity. And so everything just expands, and then it starts to contract, and then it expands, and then it contracts, and it expands, and it contracts. So everything's doing that, instead of the whole universe doing it. The galaxies are doing it. Stuff like that is falling apart at a faster rate or condensing at a faster rate. So the more the galaxies expand, the more photons they let set free, the more that is converted into a gravity, and then the more pressure there is to contract. So as they get a certain size, then there's more pressure and they'll shrink again. So something like that. Anyway, yeah, it's my simplification of process. So, but it all gets down to these simple arguments. Now, the one kind of argument that the Steve Scully he made a couple of arguments that are perfectly suitable, like this whole assuming thing, or taking one little piece of evidence and turning it into a whole theory. So, I mean, all they really have is the redshift argument and the cosmic background radiation, which he didn't mention. And it's a very little pile of evidence to base a whole theory of expanding universe on, because there could be other explanations for why distance, there's an association between how far away something is and how redshifted it is. As I've pointed out, all you need to do is have the matter hit a few atoms on the way, and have those atoms primarily moving towards you because you're moving, which makes sense. You hit more atoms in the direction you're going than you hit heading the way you're not going. I mean, heading the same way you're going, quite obviously. I mean, if you're going to hit people going into the store, you're going to hit more people going out of the store than people going in the store. That's the kind of argument, if you're going in the store. But anyway, yeah, and so that could explain redshift. Could be a simple, benign kind of explanation like that. And that truth goes for all this kind of stuff. So again, the Einstein theory, when he says the physics is same in any frame, well, not really. Okay, the physics is the same everywhere in the universe. That could be said. And so of course it's the same in every frame, but every observer is not going to see it the same, because they're going to be retarded in their perception by their connection by their association with the movement. If I'm on the train and the train's going half the speed of light, yeah, I'm going to see some things that are going to seem really strange, and I think that's the reality. So there is an absolute speed, and then things like Lorentz, these little gimmicks to prevent things from going faster than the speed of light. Well, you can make lots of arguments about why something can't go faster than the speed of light. As I'm sort of pointing out, you could create a system where your odds of hitting something are like say there's 100 things. Well, if all 100 of them are coming towards you, you can change their direction really easily by throwing something and hitting it, and it flips its direction. But as all of the dominoes, so to speak, would flip the other way and be going the same way, then your odds of hitting one is 1 in 100. So it's the needle and haystack argument. If I converted from a stack that was all needles, and then you, by touching the needles, turn them into hay, you could sort of understand there's a point where your odds of hitting a needle gets so low because you've turned them all into hay. So you can't, and so it becomes impossible for you to, let's say that there's a random conversion inside the haystack where, every 100 seconds or whatever, a piece of hay turns into a needle. That rate would end up being faster than your rate of actually touching one of them or changing them, and so you could never convert the whole haystack to needles because it's going to be turning it back into. You could never turn the whole haystack into hay, the needle stack into hay, because the needle stack will create hay faster than you can create. It'll create needles faster than you can create hay. Okay. So there'd always be a limit. And then I could argue with the ping pong paddles. If I have ping pong balls bouncing between them, I can create more and more pressure. And so that would be sort of like a Lorentz contraction in the sense that except it's a straight line. But it's a straight line that doesn't have any infinities in it. So it doesn't go to any unsustainable place, because as it gets closer and closer, the pressure does get higher and higher and higher, and nothing on the outside could ever overcome the pressure on the inside. There wouldn't be an available force powerful enough to ever compress the plates any closer than the reflective energy is creating in terms of pressure. Yeah, so it just seems very arbitrary, this Lorentz manipulations of so all of the action happens at when you're within 0.03% of the speed of light. That's when most of all this funky stuff happens, and that seems very convenient. And again, it just seems like a gimmick is what it seems like. Yeah, a gimmick that allows an infinity, that just as a matter, just as a way of thinking, what you think the universe has an infinite amount of gasoline or an infinite amount of energy, and it really doesn't have an infinite amount of energy, so why play with the idea that it could possibly create anything that would have the implication of infinite energy? Alright. This is not really getting to the specifics that I want to get to. So why don't I just get to the specifics I want to get to. So anyway, it's there's lots of little stuff. I've been playing with some words and thinking about it, but in terms of the Hothladay conversation, so I got Hothladay to at least understand the momentum argument. So I think you can see that you can create a momentum system that is very conservative, and it fits what we see. And I would argue that when you look at gravity, again, Mach gravity is essentially a momentum system, and that conservation works as long as you keep it in that closed system of just the gravity. And it breaks if you try to take it outside that system, and then you have a drag problem. And but inside the system, it works so well that it has to be considered a real contender, just because it explains so well why things are spherical and why there's an inverse square law. It spells it out, and it does so with a simple mechanism of push rather than a complex mechanism of pull. It also acknowledges what we, in a sense, what we could understand is that this idea of energy coming from nothing, that is coming from the center of something with no fuel, doesn't make much sense, where we can sort of understand the idea of the external world having all kinds of stuff that could be happening where it could be creating pressure. We see that the suns burn we see the whole universe shining a little bit, which means that's all energy hitting us. And so the idea of that system having the capacity to compress us makes a hell of a lot more sense than thinking that somehow we're pushing on it, through some pulling on it, through some mechanism of force, unforce. I don't know. Yeah, it's just impossible to make sense out of that when you really think about it. Well, anyway, and then the big subject is gravity. I've sort of, like I said, the mock gravity does explain it, and I've given you the added bit of explaining the inductive part, the idea where gravity really is, it has no function without the actual movement. If things don't actually move into each other, it ain't going to happen. You have to absorb a force for something not to be hit by it. And that's the key to gravity, is that the force is absorbed. That's what momentum and movement is the absorption of force. You've owned it, you've trapped it, you've taken it, and now it doesn't go somewhere. So that simple argument, I think, is just no, you can't defeat it. It's too sensible a way of understanding why things move. Is that if you're going to move, it means you had to, you're occupying something. Something is busy moving you. And that thing isn't where it would have been if you weren't moving. If you weren't using it, it would be going somewhere else. And obviously the somewhere else is going to be saying, I'm missing something. And then it's going to move again. And so it's all inductive. I think that's a solid argument for gravity. And then the magnetism argument is just so good. I mean, once you have the two forces, and the inverse relationship between the two matter bits, in terms of the two reactions, the reflection that ends up being an absorption and a readmission, but anyway, but in a sense it's just a reflection and an absorption of momentum, and the other where you just change the direction of the force, you just divert it, and having those two functions, and it perfectly fits for what a magnet's doing in terms of it's just a filter. An external force comes in and it makes that force so much more powerful by segregating it into a proton heavy force and an electron heavy force. And that kind of subtle polarization, which is a dangerous word. See, a lot of the words here are just so broken that this is what makes it hard to even discuss these things. And I was just, as I was listing words, I'm just saying, yeah, we don't have words, for making good sense of this stuff. So I thought about it. I said, okay, yeah, I'm going to have to call it electron force and proton force. It's the only way, because it has to be connected to the electron and the proton, because that's the matter bits that are the most significantly charged objects, and that's the only way to really understand it. And again, the whole function of charge and electricity is clearly a byproduct of this, as well as magnetism. It just draws all those things right into each other. You can't separate magnetism from electricity, and the only distinction is the creation of the dipoles versus monopoles. Electricity is monopoles. Magnetism is about what dipoles do, and that's all the difference there is. So, yeah, so I just think on those two grounds, I mean, the beautiful explanation of gravity that can be done with an external push force. Magnetism and charge and electricity end up looking, just completely understandable once you understand there's two forces to go with the two charges. The two matter bit charged. There's a plus and minus force. It's just that simple, just as there are plus and minus matter bits. And everything fits together, just all fits. The conservation of momentum, the idea of absorption and reflection as being the only real functions, and it's essentially attraction and repulsion. If you don't reflect, okay, you can't repel. But if you are reflecting whatever comes at you, and this is a fight with arrows or bullets, you can understand if every time somebody shoots you, the bullet bounces off you and hits them, you can understand that, that's very effective. And it hits them and comes back to you and bounces off you again, hits them again. And it bounces off you and hits them again. You can sort of understand how that's tremendously effective in creating motion. There's your strong repulsion that you see with magnets, and the attraction is merely the absence of that, and then you have a collapsing force because the external pressure is going to be greater than the internal pressure as soon as anything moves. If this moves towards this, and this had to absorb the force to move, you can just get it that this has to feel less force here than it feels here, and it has to move. And when it moves, it absorbs force going this way, and so now this thing's getting hit by less. It's just, you can't deny it. And be reasonable, in my opinion. Alright, so, so this video didn't go exactly where I intended. I just don't know if there's any point in me doing any actual drawing or arguing for these specific things. It's just these general subjects. I think I just think I think I should be able to explain this now in without too much work, and just make it so, do this simple comparison. Look, this is what they're saying. Look how simple this answer is. Because the Steve Scully guy, he's got all this stuff swirling around. He's magical gravity forces creating figure 8 patterns. Again, the same thing with the magnets. He takes the picture of the field lines, and again converts this into some sort of stuff that's actually flowing in these, and there's no evidence of it. None. There's not a single experiment on Earth that will demonstrate any of this motion around a magnet. A sitting magnet doesn't have any of this stuff moving around it. There's just no evidence of that movement. And all you have is this little subtle motor force, where it either goes up or down, the way they flip. And they flip by a simple rule, but there's no evidence of any swirling motion that any ether or any other, and again, even as soon as you start with this swirly spinning stuff, the amount of energy you need to make the spin is so much more for the amount of attraction you're going to get out of it. You're going to get a tiny 1/1,000,000th of the amount of energy out of that you had to put into the system. And it just seems sort of crazy for people to think the universe would have an attractive mechanism that required 1,000,000 times more energy to create a tiny movement. Like the universe wouldn't just throw a brick from point A to point B, and instead it would use 1,000,000 times more energy to swirl the brick to some other location. No, I don't think so. Alright, so I don't know if there's so yeah, I want to do some writing, and I gotta do some videos where I just want to get just isolate the concept. So I'm thinking, what subjects are important to Hoffaday? So I guess what I got to find out, right? Because I think the magnetism one, he's got to understand that one. That's solid. We already did the momentum thing and gravity, so he should get that. So what we got left? Drag argument. Now I've sort of made the drag argument. It's a little bit more. You got to understand how atoms work a little bit, but it's not too complicated. And what else is there after that? I mean, he's conceded that the multitasking argument to explain time dilation, the fact that clocks don't function the same way when they're moving. And I think I've given so many examples also of just how obvious it is that there's things are really changed when they're moving. These two flashlights, if one was going 50,000 miles an hour through space and one wasn't, what's that? Stupid sounds. Anyway, this whole idea that it's not a mystery that you could say that it doesn't go 50,000 miles for no reason. Something had to make it do that. Something had to impact it. You know, a big fire had to come out of it. Some kind of thing had to happen for it to exchange parts and do all this stuff to make it go. It's going for a reason. That there's a physical difference between the one not moving and the one moving. The bullet in a box on the shelf is fundamentally, physically different than the bullet just fired out of a gun. They're physically different. They've been changed by acceleration. And we all know that feeling. We can feel how acceleration in a car, anywhere, how we can feel it changing us. We can feel the process. So why deny it? Why deny that nothing's changed? That you're physically the same, no matter what speed you're traveling? You're not. You're changed. We feel it when we're accelerating, because that's where the change is being imposed. And once you have the new velocity, then you settle. You acclimate to the velocity. That's what we do. That's what we have to do, frankly, as organisms on the Earth. Is that we've learned to do that because of, frankly, gravity changes. The moon actually changes the gravity on the surface. And we have evolved on this planet, and that's why we're capable of changing. Because the planet's different locations have different gravity, different amounts of pressure. So yeah, the organism that adapts wins. So we have some capacity to adapt, but it's limited. And I think most people can understand that you're going to get killed. If I force you to accelerate too fast, I'll kill you. So clearly velocity is something real happening. To gain speed through this accelerating process can kill you, because the change is so significant. It's not an insignificant change, it's a significant change in your material structure. You're not the same flashlight anymore, or bullet, or space shuttle. And I don't know how anyone can deny that that's really got to be where the truth lies. There's no magic. You just jump into a frame and you know, velocity is irrelevant and always relative. No, it's a real thing, and it really affects physical things. So it affects atoms in terms of their decay, and it will affect bigger physical things in ways too, where their function will deteriorate. Now, it's not going to affect them all in the same way, and there's not going to be this perfect Lorentz curve of change. I think that's a silly expectation, but whatever. It seems obvious. It seems well logically sufficient. I don't know. It seems of the available options, it seems the most reasonable to accept that the reason why acceleration feels like something is because it is something. It's not free velocity. You just don't have it for free. It's a process, and the process is not trivial. Yeah. So that was one of the Steve Scully things he puts in his book way too often. You know, the Walter Lewin line, not trivial. You know, I don't know who did it before Walter Lewin, but it just, you know, it's the, you know, did people just want to make important sound more important, so then they say non-trivial. Yeah, just to, you know, just so they don't say important too many times. It's very important, and you know this. Or it's not a non-trivial point of contention. You know, so you know, it's just a way of saying it backwards. Which I guess, you know, physics is doing, you know, all this anti-particle stuff. It's just backward physics. So anyway, so maybe I'll do some of this Steve Scully guy thing. Eventually, if he gets to something where there's an actual, you know, some kind of real conversation about what we really see, you know. But I don't know. It's just a lot of, you know, it's not really getting to the physics. So the first two chapters, well, 3 chapters, there's just not enough physics. It's just some conversation about how to think about physics. So it's too general, and it's again all on points that I don't think can possibly be. First off, the infinity thing, I can't see how it could possibly matter, and the dismissing the significance of charge, I think that's just a non-starter. You're not going to get anywhere. So many holes you're never going to come up with a theory of electricity and magnetism if you don't recognize charge. You're just done. You're hopeless. Because that swirly crap isn't going to account for it. Alright, anyway, that's probably enough of a video, because I don't really feel like doing more. Yeah, I guess that's the truth of it. I'm tired. So I'll just leave it here, and maybe if I wake up, drink some tea here, then I might want to take on some of these subjects, but probably what I should do is just keep messing with vocabulary and see if I can find the right vocabulary to make things really clear. But it's like this, momentum, acceleration, velocity, weight, mass, imbalance, pressure. I mean, these are the key things. Push, again, just so obvious. But I mean, yeah, you can just tie all these words together. I mean, to have momentum, first you have to have some mass. You have to accelerate the mass, so it acquires a velocity, which gives it more mass in a direction, okay, which is essentially the definition of momentum. So, I mean, mass in a direction, that's momentum. Having more mass in a direction, it's momentum. So anyway, yeah, so till the next time and such, I think I'll just leave it there and just do this kind of stuff. It's fun. Yeah, I could. So I have to do some drawing later. So anyway, yeah, I like this. This is a nice little program, but the problem is it just randomly crashes. It's not the blue screen of death, it just freezes. So that's a little irritating. I think it's just, I don't know. I think there's just something about the computer that's doing it. Because the Linux Mint freezes too, so I just can't, yeah, so I don't know. Maybe I shouldn't use this computer. Yeah, but I want to use it. So anyway, yeah, whatever. Yeah, it's my computer. I want to use it. It mostly works. Anyway. So, yeah, I have computers that do certain things really well, and then the other computer does a certain thing really well, and then the other computer does something really well, but not one of them does everything well. So it's that kind of problem. But anyway, till the next time and such. Yeah, I think that's really enough.